Hello students, uh, welcome to the class of high voltage engineering. So we have started our discussion with generation of high voltages and currents, in which uh, till date we have discussed or we have seen the various methods or techniques used to generate high voltage DC and high voltage AC at power frequency in the high voltage laboratories for the purpose of testing the insulation and the equipment's performance under the presence of over voltage magnitudes. Today our agenda is to discuss about the Tesla coil or the doubly tuned resonant transformer, which is used to produce high voltage AC at high frequency. So now here, that what is the necessity of generating high voltage AC at high frequencies? So my friends, we all know that the insulations that are being used in high voltage equipments are not only designed to withstand the high voltage magnitudes at power frequencies, but they are also designed to to withstand their electrical performance or electrical behavior under the presence of the over voltage magnitudes of a shorter duration or over a longer duration, which have the frequency other than the power frequencies. So it is necessary to evaluate the performance of the insulation and that of the equipment is very important under the presence of high voltage high frequency supply. So to meet with this criteria or to evaluate the qualitative performance of our high voltage equipment under these transient voltage conditions, the high voltage AC at high frequency is generated in high voltage laboratories. The another requirement of using these Tesla transformers or doubly tuned resonant transformer is to study the spark phenomena. Okay, we all know that when the potential surrounding the conductor exceeds the corona inception level, there always be the ionization of the air, and as a result there will be the formation of the spark. So if suppose we want to determine the length of the spark, then it needs the generation of this high voltage AC at higher frequency using the Tesla transformers. So for the purpose of studying the arc, it needs the high voltage high frequency supply. So this can be achieved by using this doubly tuned resonant transformer, usually known as Tesla transformer, which was invented by Nikola Tesla. So let us see uh, the points which we have already discussed till so far. Then we will proceed with our main objective of today's lecture. So we have seen the high voltage DC generation techniques, which includes half wave and full wave rectifiers. Then we have seen voltage doubler circuits, voltage multiplier circuits, electrostatic generators, in which we have touched upon the Van de Graaff generators. Generation of high voltage AC at power frequency, in which we have discussed the testing transformer, cascade connection of transformers, and resonant transformers. Okay, so today our agenda is to discuss about how the high frequency high voltage AC can be generated in high voltage laboratories. So one is the Tesla coil, second is impulse voltage generator. So Our discussion for today's lecture is Tesla coil. So let me show you the video to enlighten the history of this Tesla coil and how it was invented and for what purposes, so that you can get a better idea.
Inventions. The Tesla Coil, 1891. The inventor, Nikola Tesla, had dreamed of supplying the world with electricity wirelessly. Tesla developed a device in 1891 which could produce bolts of high-voltage electricity, known as the Tesla coil. The device has a primary coil which passes a current onto a secondary coil, creating a high voltage and low current, which shoots out a lightning-like discharge. Tesla put on demonstrations showing how the Tesla coil could be used to power light bulbs wirelessly nearby. He also held the light bulbs up close to the Tesla coil, powering them without harm to himself. From 1899 to 1900, Tesla built a new laboratory in Colorado Springs, and it is here that he built a larger version of his Tesla coil called the magnifying transmitter. It measured 51 feet or 15.5 meters in diameter and could reach outputs of up to 12 million volts. With this version of the Tesla coil, the inventor could light up 3 incandescent bulbs at 100 feet or 30 meters away. One night, the magnifying transmitter overloaded during an experiment, burning out the power station and turning the town dark, terrifying the locals. In 1901, with funding from businessmen, Tesla built his next larger transmitter, this time in New York, named the Wardenclyffe Tower. Tesla had acquired the investment by pitching his proposed world wireless system as a way of communicating across the world by broadcasting messages, as well as delivering electricity wirelessly. Physicist and radio pioneer Guglielmo Marconi would send the first Atlantic wireless transmission in 1901 using Tesla's ideas, but Tesla was not interested in wireless messages as much as wireless power. Nevertheless, while wireless messaging worked, there was no proof that wireless power could work beyond a short range. By 1904, Tesla's investors had pulled out, and with staggering debts, the Wardenclyffe Tower was eventually demolished in 1917. In the early 20th century, the Tesla coil would be used for a number of things, including radios, medicine, X-rays, electrotherapy, and for entertainment. But in the present day, the Tesla coil has been replaced by more modern circuitry. Subscribe for more history.
So now I think you get to know about the history and history about the invention of Tesla coil, as well as the video has nicely represented the sort of the applications where the Tesla transformers can be adopted. In addition to that, I want to add one point that you can also found the existence of this high frequency, high voltage AC equipment when you open your television. Okay, so you have a cathode ray tube CRT. Okay, so it needs the high frequency signals. So the solid state Tesla coil you will found when you open your television. Okay, so the video has nicely explained about the some sort of the applications where you find the existence of this Tesla coil. But as video represented that the Nikola Tesla was enthusiastic to invent the wireless power transmission. Okay, so he was more interested in the power transmission rather than the broadcasting of the messages. But if we are thinking of the wireless transmission, then you need to consider the several kinds of factors. Okay, ultimately we are trying to transmit the electrical power and electrical power without using any wires. So we can consider that there always be the transmission of the electromagnetic field waves. Okay, so it may be dangerous to the human bodies, it may be dangerous to any living bodies on this planet. So idea was actually dropped out to transmit the huge amount of power without using any conducting system. Okay, so generally, by considering the so many drawbacks associated with this wireless transmission system, the Tesla coil, or the this high frequency, high voltage AC based WT-net resonant transformer is stick with the radios and this electronic circuitries and all. So Tesla coil, okay, is an electrical resonant transformer circuit. Okay, so it obviously operate on the principle of the parallel resonance, and it was invented by Nikola Tesla in 1891. So it is used to produce high voltage, low current, high frequency alternating current electricity. So here you can see in the photograph that uh, how the Tesla transformer looks like. Okay, so in the high voltage engineering laboratories, generally the Tesla coil is used to study the arc behaviors. Okay, so ultimately you can see over here the spreading of the arcing channels is nothing but it is a transmission of the electrical power. So now you can think that if suppose you want to transmit the huge amount of power using this conductorless technology, then you can imagine the problems. The Tesla experimented with number of different configurations which consist of either the two or sometimes three coupled resonant electrical circuits. So if you are considering this Tesla transformer, then you have the one sort of loose coupling between the primaries and secondary windings. Okay, so I will discuss the some of the differences between the ordinary transformers and the Tesla transformers. Okay, other than the differences, the operating principle of the Tesla coil will remain similar to the operating principle of the uh, ordinary transformer. Okay, by considering the Faraday's law of electromagnetic induction, but the mode of stepping up the voltage is somewhat different in Tesla transformer. So Tesla use these circuits, means the two or sometimes three coupled resonance circuits, to conduct the innovative experiments in electrical lighting. Okay, then the X-ray generations, the high frequency alternating current phenomena, electrotherapy, and so on. Okay, so the investigations normally conducted without using any kind of physical connections between the two circuits. Okay, so completely it was wireless. Tesla coil circuits were used commercially in spark gap radio transmitters for wireless telegraphy until 1920s, and in medical equipment like electrotherapy and violet ray devices. So today, as video has discussed, that their main uses is for entertainment and educational displays, although small coils are still used as a leak detector in high vacuum systems. So let me see the difference between our ordinary transformers that we are using for the transmission of the power or the distribution of the power with respect to the high frequency, high voltage AC generator, broadly named as a Tesla transformer. Okay, so in case of the ordinary transformers, normally you found the two coils. One is the primary winding and the secondary winding. So similarly, in the case of Tesla coils, again you have one primary winding and secondary winding. But in Tesla transformers, the primary winding turns are usually up to 5, and they are made up of a very thick conductor, whereas the secondary winding of the Tesla transformer consumes so many tons and made up of a very thin wire. Okay, so considering the design of this primary and the secondary winding, it is completely different. So ordinary power transformer, as you can see that the winding is normally placed on the iron core, okay, which acting as its magnetic circuit. But in case of the Tesla transformer, normally the insulating formers are used to keep the windings. Okay, now the reason is why we do not go with this iron core structure, because the intention is to produce this high frequency signals, and as the Tesla transformer adopts the resonant condition, it obviously produces the high frequency signal, so it may cause the saturation to the magnetic circuit. Okay, and the magnet once the magnetic circuit gets saturated, it will introduces the enormous kind of the harmonics. So to prevent the saturation of the magnetic core, generally the air core or the insulating former based kind of core is used in case of the Tesla transformers. Okay, the another requirement of the iron core in the ordinary transformer is to obtain the tight coupling between the primary and the secondary winding. Okay, so whereas in case of the Tesla coil, as there is the insulating former between primary and secondary, the magnetic coupling is very weak. Okay, you can simply consider it as a magnetic isolation. So if we are considering the coefficient of coupling for the Tesla transformer, then it is roughly around 0.05 to zero point 0.2. But in case of the power transformers, due to the inclusion of this iron core and having the tight coupling between this primary and secondary winding, the coefficient of coupling is considered to be 0.95 to zero point 0.98. So in case of these power transformers at high frequencies, normally the energy losses will be assumed to be more, like the eddy currents or the hysteresis, so it is not used in the Tesla coil. Okay, so again there might be the problem of the overheating if the high frequency signal is present. So generally the Tesla transformer avoids the use of this iron core circuit. The ordinary transformers are designed to have the tight coupling. So tight coupling is supported by the use of this iron core, whereas the Tesla transformer in contrast is loosely coupled because the insulating former is used. The Tesla coil works on the principle of parallel resonance. So we will see that how this resonance condition is being achieved in the Tesla transformer. Tesla coil is known as a doubly tuned resonant transformer. So as it operates on the principle of this parallel resonance, so that is why it is known as a doubly tuned resonant transformer. Okay, so in case of the power transformers, usually the two coils are mutually coupled. One is primary and second is the secondary. Whereas in case of the Tesla transformer, you have the flexibility to couple the three windings or even the two windings, means two circuits or the three circuits you can couple simultaneously. So here you can see this is the equivalent circuit. The figure A represents the equivalent circuit of the Tesla transformer, whereas when you are connecting the CRO at the output terminals or across the secondary of this Tesla transformer, then you will have this kind of damped oscillations, high frequency damped oscillations, okay, as an output. So Tesla coil is a doubly tuned resonant transformer. So here you can see this L1 represents the primary side and L2 represents the secondary side. So the primary voltage rating of this Tesla transformer is usually up to 10 kilovolt, whereas secondary depends upon the number of turns. So it may vary from 500 kV to 1000 of kV. The supply may be AC or DC. So based on the type of the supply voltage, the Tesla coil is divided or classified into the two parts. One is known as AC Tesla coil and second is known as a DC Tesla coil. Okay, so the supply is generally used to charge the capacitor C1, which is known as a primary tank capacitor. The spark gap G, as you can see over here, this is normally a one type of the sphere gap assembly which is connected across the primary of this Tesla transformer to trigger at a desired voltage. So once it gets triggered, it will makes this C1 in parallel with the L1, so that to obtain this parallel resonance condition. Okay, so once the spark gap across this primary circuit gets triggered at a desired voltage, induces a high self excitation in the secondary because of the close proximity of primary and secondary winding to enable the tight coupling between the two coils. But because of the insulation former or due to the air core, there always be the some amount of energy loss has been observed between the primary and the secondary. That is just because of the loose coupling. Okay, so once we place these two coils close to each other, we can have the self excitation in the secondary. When the spark gap at the primary side gets triggered and makes the capacitor C1 in parallel with L1 to enable the parallel resonant condition. So once this parallel resonant condition has been satisfied, it will produce high frequency damped oscillation, as you can see in the waveform. So primary and secondary windings L1 and L2 are actually wound on insulated former with no core, or usually known as air cored, and are immersed in the oil. Okay, so why they need to be immersed into the oil? Because due to the higher frequency, there always be the heat losses. Okay, so tremendous heat can be generated. So to offer the better cooling as well as the insulation to these current carrying parts or the current carrying winding, the liquid dielectric is used. So the main function of the liquid dielectric is to keep the windings L1 and L2 cool. The windings are tuned to a frequency of 10 to 100 kilohertz by means of this capacitor C1 and C2. So C1 is usually we can see in the circuitry, but the C2 is actually representing the stray capacitances. Okay, so stray capacitances, it means that the capacitance which you imagine between the high voltage terminal of the Tesla coil and the ground. Okay, so there is the stray capacitance. Okay, so here it is represented by C2. Okay, so in more general way, the circuitry of the Tesla transformer is represented like this. So here you can see the C2 is a stray capacitance, that is with respect to the ground. Okay, it is between the high voltage secondary terminal of Tesla transformer with respect to the ground. So it normally represents the equivalent capacitances. Okay, series parallel capacitors. So let us see that how exactly it works. Okay, here this T represents the supply transformer. So the current from this supply transformer will charge this capacitor C1. Okay, you can represent this side, this primary side, either to this or to this. Okay, in both the way it is correct. So current from the supply transformer will charge the capacitor C1 to a higher voltage. Let us assume that the input voltage to the C1 is 30 kV. Okay, now I want to charge this capacitor to 30 kV value. So what should be the length of gap between the two spheres or the rods? It should be somewhat more than 1 centimeter. Okay, so once I'm keeping this keeping the length between the two electrodes of the spark gap somewhat higher than 1 centimeter, then it will allow me to charge this capacitor C1 to 30 kV. Okay, otherwise what happens if the length of gap between the two electrode is lower than 1 centimeter, then you cannot achieve the full excitation across this capacitor C1. Okay, so always you always capture the premature operation of this Tesla coil. So ideally, in other way, I can say that if the spark gap is adjusted lower than the maximum voltage of capacitor, then at the output side we will get the voltage magnitude lesser than the expected one. So during the charging phase of this capacitor C1, usually the length of gap between the two electrodes of spark gap is considered to be somewhat higher than its breakdown voltage value. Okay, so here for an example I have written 30 kV. So the spark gap should be adjusted somewhat larger than 1 centimeter, so that it will allow to charge this capacitor C1 to 30 kV. So when the voltage across this capacitor, okay, when the voltage across the capacitor becomes 30 kV, we need to adjust the spark gap. So in this case you have the manual operation as well as the automatic operation. So to obtain the automatic operation of the Tesla transformer, usually the length of gap is adjusted to its breakdown voltage value. So when I'm keeping it as 1 centimeter, and when the capacitor will charge with a voltage level of 30 kV, it will be automatically triggered. So when the voltage across the capacitor will reach to the breakdown voltage of the spark gap, the spark is initiated, which close the switch, okay, which close the switch due to the reduction, close the switch and makes this C1 in parallel with L1. So this will complete the primary circuit, and current from capacitor will now flow from capacitor to the primary coil inductor. So current will flow rapidly back and forth between the plates of capacitor through the coil and generating a radio frequency oscillating current in primary circuit at the circuit's resonant frequency. So ultimately, once we are assuming that the spark gap is getting triggered off, then the C1 comes in parallel with L1. Okay, so capacitor will now come in parallel with the inductor. So whatever the energy has been stored by this capacitor will now discharge to charge this inductor. Okay, so now capacitor will delivers the charge to the inductor. As an effect, the inductor will fully charge. Okay, again, once the inductor is fully charged, it will deliver its charge to charge the capacitor again. So there is a transformation of the energy between the capacitor and the inductor continuously, which result in the generation of the radio frequency oscillating current in primary circuit because of the resonance condition. Okay, as the frequency is changing, so at some position you can obtain the resonance condition where XL becomes equals to XC. As a result, it will produce the high frequency AC signal in the primary circuit. So this oscillating magnetic field of primary winding induces the oscillating current in secondary winding L2 due to the Faraday's law of electromagnetic induction. And to achieve this, the secondary coil is normally placed very close to the primary circuit. Okay, so if the primary winding and the secondary windings are placed very far, then there is no magnetic induction or magnetic coupling will be observed between the primary and secondary winding. As a result, the output voltage will remain zero. Why? Because whatever the energy has been produced or has been captured in the primary is completely lost. Okay, so to offer this Faraday's law of electromagnetic induction principle, the primary and secondary windings are normally placed close to each other. Okay, though there is a small amount of energy loss because of the insulation former, but yes, the induction would be there, which will allow the generation of the oscillating magnetic field into the secondary. Okay, so now here you have this oscillating magnetic field which links with the secondary coil and induce the EMF. So over the number of cycles, the energy in primary circuit will transferred to the secondary. I will show you the waveform that how it will be transferred. Okay, so I think you understand that how it will be transferred from primary to secondary. It obeys the Faraday's law of electromagnetic induction, and usually because of the close proximity of the primary and secondary winding, the magnetic coupling is present. So because of this magnetic coupling, the primary energy has been transferred to the secondary side. So the total energy in the tuned circuit is limited to the energy originally stored in capacitor C1, so as the oscillating voltage in secondary increase in amplitude, which is known as secondary ring up, and at the same time the oscillations which are captured or available in the primary will decrease to zero, which is known as primary ring down. So here you can see in the first phase, so this first phase will indicates a primary ring down, that will represent the transformation of the energy from primary circuit to the secondary circuit. So once the energy stored in primary circuit is transferred to the secondary, you observe there is a buildup of the voltage. So this process, the second phase of operation, is representing the waveform that you are usually seen to the secondary side, and that is known as a secondary ring up. So this initial stage is known as a primary ring down, because now as the energy is transferred, from primary to secondary, the value of the magnitude of energy associated in primary circuit is reduced to zero. Okay, so the point, let me show you in a very precise manner. So let us consider this wall time characteristic. So initially the energy has been captured into the primary circuit. Now due to the coupling between primary and secondary coils of Tesla transformer, the energy is transferred from primary winding to the secondary winding. So this phase represents the transformation of the energy from primary to secondary winding. Okay, so here there is a reduction in the primary energy. So this is known as a primary ring down. Okay, and the point at which the energy in primary winding achieves zero value is known as a primary notch or first primary notch. The second is at the same time as now this energy from primary is being transferred to the secondary winding. According to the Faraday's law of electromagnetic induction, the EMF is induced. It means that you will observe the increase of the voltage. Okay, so the rate of rise of the voltage is normally depends upon the number of turns available into the secondary winding, as well as how the secondary winding been placed close to the primary winding. So here now you can observe over here the voltage value at the secondary side is building up. Okay, so this is known as a secondary ring up, because the voltage in the secondary winding is increased. Okay, so now as there is a proximity between the primary and the secondary winding, so whatever the energy has been gained into the secondary winding is now reflected back to the primary winding. So the energy is now transferred back to the primary because of the mutual coupling between the primary winding and the secondary winding, which enables a secondary ring down, and at the same time the energy in the primary winding increases, which is known as a primary ring up. Okay, so process is continuously observed, and there is a one state that where the capacitor will discharge its energy. As a result, the potential across it becomes lower than the breakdown voltage of this sphere gap. So under that circumstances, the spark gap will get open circuited and behaves as an open switch. So under this situation, now the transformer will deliver the energy to charge the capacitor. So this is how the Tesla transformer is usually working. So although the ends of secondary coil are open, it also acts as a tuned circuit due to the capacitance C2. So sum of the C2 will actually represents the sum of parasitic capacitance or the stray capacitances between the turns. Okay, usually it determines the series capacitances plus the capacitance of toroid or the electrode E, that is this. Okay, so this will so C2 represents the equivalent capacitance. So once it gets charged, the current flows rapidly back and forth through the secondary coil between its ends. So usually C2 is in terms of picofarad, whereas C1 is normally in terms of microfarad. So C2 is very, very small. Okay, so the oscillating voltage across the secondary coil which appears on output terminal is much larger than the primary voltage. So I will show you the equation from which you can calculate the secondary voltage, and from that equation you can get to know the influence of the stray capacitance on the magnitude of the voltage. The secondary current creates a magnetic field that induces voltage back in the primary coil, as I have already discussed to you, and over a number of additional cycles the energy is transferred back to the primary. So successively these processes continue until the voltage across this sphere gap becomes lower than its breakdown voltage. So once the potential across this sphere gap becomes lower than its breakdown voltage, it will acting as an open switch, and once it acts as an open switch, there is no transformation of the energy has been observed between primary and the secondary winding. Okay, so the process is then repeated. The transformer will supply the energy to charge the capacitor to a Vmax value, and once the voltage across the capacitor becomes more than the withstanding capacity of the spark gap, the process starts repeating. So this process repeats, the energy shifting rapidly back and forth between the primary and secondary tuned circuit. So during the transformation of energy from primary to secondary and from secondary to primary, the potential across the spark gap gets reduced because of the loss of energy during the transformation. The oscillating current in the primary and secondary gradually die out due to the energy dissipated as heat in the spark gap and resistance of the coil. So when the current through the spark gap is no longer sufficient to keep the air in gap ionized, the spark stops or quenches, terminating the current in primary circuit. So oscillating current in secondary may continue for the some time, and after some amount of time, the energy in the secondary reduced to zero. Okay, so the current from the supply transformer begins charging the capacitor C1 again, and the whole cycle repeats. So this is how the Tesla transformer works. So the output voltage V2, which is a function of the parameters L1, L2, okay, L1 that is the primary winding inductance, L2 secondary winding inductance, C1 primary tank capacitance, which is usually in microfarad, and capacitor C2 which is in picofarad, and the mutual inductance M. So the output voltage is a function of all these parameters L1, L2, C1, C2 and M. So usually the winding resistance will be small and it only contribute for damping of oscillations. The energy stored in the primary circuit in capacitance C1 is transferred to C2 via magnetic coupling. So whatever the energy has been stored in primary circuit is transferred to the secondary circuit by means of the magnetic coupling between primary winding and secondary winding. So if we are considering W1 is equal to W2, okay, if suppose W1 be the energy stored in capacitor C1 and W2 be the energy transferred to C2, if we consider the efficiency of Tesla transformer as eta, then the relationship can be written like this: W1 is equal to 1 half eta C1 B1 square is equal to 1 half C2 B2 square, where eta determines the efficiency of the transformer, and the efficiency of the transformer will further depends upon the magnetic coupling exists between primary winding and secondary winding. So the efficiency of the Tesla transformer can be increased by placing a secondary winding close to the primary winding. So based on this formula, based on the energy equations, we can determine the magnitude of output voltage. So V2 is equal to V1 into root of eta C1 upon C2, where C1 is in terms of microfarad, whereas C2 is in terms of picofarad. So if we are considering input voltage as supposed to be 10 kilowatt, and the efficiency of suppose 90% or 90%, C1 is suppose 0.1 microfarad and C2 as 1 picofarad, then you can imagine the magnitude of the output voltage that you are getting with the available Tesla transformer. It is in terms of the megavolt. So you can also design your own Tesla coil for your high voltage laboratory. So let me show you the video that how you can develop, or you can make you can design your own Tesla coil for the demonstration purpose. So this is how you can make your own Tesla coil at home. So let us see the applications and the advantages of the Tesla transformer. So application wise, high frequency, high voltages are required for the rectifier DC power supplies, and for testing electrical apparatus for switching surges, high frequency, high voltage damped oscillations are needed. Okay, so to study the behavior of the high voltage equipments under the presence of over voltages of the longer duration, okay, like the switching surges, you need high frequency, high voltages. So uh, apart from the impulse voltage generators, you can also uh, produce the required longer duration over voltages with the help of the Tesla transformer, but they need a better protection towards the equipments as well as the person who is conducting the testing using this Tesla transformer. Okay, so considering the utilization of these Tesla transformers in high voltage laboratory for the purpose of testing is actually too much dangerous. So that is why the impulse voltage generators are normally preferred to use to produce the over voltages of longer duration and the shorter duration. So advantages of the Tesla transformer, the absence of the iron core in transformers and hands, there is a saving in cost and the size. It will give us the pure sine wave output, slow buildup of the voltage over a few cycles, so no damage occur due to the switching surges. Uniform distribution of the voltage across the winding coils due to subdivision of coils into the stack of number units. Okay, so it will provide a better degree of uniformity of the electrostatic field stresses across the each stacks. So it provides a better safety to the insulation of the winding itself. So these are the advantages of the Tesla transformer. So in the next lecture, we will see the uh, impulse voltage generators. Okay, so this is also a one set of the equipment which is used to generate the high voltage AC uh, AC uh, at the different frequency magnitude. Okay, so generally the impulse voltage generators are used to produce the lightning over voltages as well as the switching over voltages, where we can avoid the uh, effect of this electromagnetic field waves which we normally observe with the Tesla transformer. So in next lecture we will see these single stage impulse voltage generators and the multi stage impulse voltage generators. Thank you.